Welcome back, folks. It's me, Mr. Hess, again, ready to show you another section of Chapter 9, which is all about circles. In our second section, 9-2, it's titled Angles and Arcs. So behind me here you'll see is a picture of a circle. And some terminology I want you to know about circles. First of all, if the center of my circle is here at P, then anytime we make an angle that goes right to the center, or in other words has its vertex at the center, then this angle here, which we would call APB, is called a central angle. You know, the name makes sense. After all, its vertex is at the center of the circle. So this would be a central angle. Okay, and the reason I'm pointing that out is because when you draw a central angle, you'll notice as you draw the angle, it goes out and hits the circle at a couple spots, and it cuts that circle into some parts. And part of a circle, like from here to here, is what we would call then an arc. A-R-C, arc. It's kind of like, electricity, how sometimes electricity will jump from one end to another and form an arc. Okay, but arcs then have certain measures, and the measure of the arc is in degrees, just like an angle would be. And in fact, the measure of that arc is determined by its central angle. For example, let's suppose that I knew that this central angle APB, so the measure of angle APB is 60 degrees, let's say. So that's 60 degrees. Okay, well, if a central angle measures 60, as it goes out and hits the circle and creates an arc, which we often refer to then as the intercepted arc. That's just a fancy way of saying that where the angle intercepted the circle, it created that arc. So that intercepted arc, which is then referred to as arc AB, is written, first of all, notarized like this. You put a little symbol above it of a little miniature arc. Notice it's not a segment, it's bent. That's curved, just like the arc is. Okay, so that's how you write an arc. And if you want to refer to its measure, just like on an angle, you put a little M in front of it. So the measure of this arc AB would also be 60 degrees. So the arc will be the same measure as its central angle. When you think about it, you could sit here and draw central angle after central angle after central angle, slicing this up into kind of like pieces of pie. When you cut up a pie, at Thanksgiving dinner, for example, you always cut from the center out, so it creates all kinds of central angles. So these are all like slices of pie, which we've talked about before, are known as sectors, in fact. It creates different sectors. But whatever the central angle is, then is also the measure of the arc. Okay, so I'm going to give you some more measurements here. First of all, I'm going to label this C and D, and I want you to see that BD here is a diameter. Okay, so BD is a diameter. Diameters are good because, not only are they have their own special name because, they're the longest chord you can make in a circle, but of course they cut the circle in half. If you think about it, what should all the angles at the center here, if I work my way all the way around, one full rotation, what should all those add up to? Well, one full rotation, of course, is, yeah, you guessed it, 360 degrees. So that's what all these arcs out here should add up to as well. Because again, the central angle is going to match, or the arc's measure is going to match the central angle. So let's say, for example, that I told you that this angle here is only 30 degrees. Okay, now you should be able to start giving me the measures of some arcs up here. If I said, okay, what's the measure of arc BC? Okay, you see its central angle is 30, so of course the arc itself is also 30 degrees. arc CD. See, it goes from here to here. You should now be able to find that one as well. Should be able to find the measure of arc CD. Now you're going to have to do a little math here. Remember, a diameter does cut a circle in half. So if a full circle is 360 degrees, half of a circle is going to be 180. And if this part's 30, 30 plus what is going to give you 180? Or in other words, subtract 30 from 180, and you're left with 150. So there's arc CD. It is 150 degrees. Okay, and then finally, we have the arc DA here. See that one? That's one of the few measurements I haven't found yet. Again, I can find the measure of that arc because, again, not only did this diameter cut this bottom half into 180 degrees, but the top half should also be 180. So this time I would take away not 30 but 60 away from 180, and that's what should be what's left over here. So when we do that, we're left with 120 degrees for this arc DA. And as you can see, then I've found all the arcs that make up the full 360 degrees of the circle. Now, every one of the arcs that I found here are referred to as minor arcs. Okay, a minor arc is, simply put, it's an arc that is less than half the circle. Or in other words, it should be less than 180. 180 degrees, of course, being half of a circle. Okay, so you can see all those were, less than 180. Every arc up here that I have labeled with a measurement are all minor arcs. Okay, but of course, as you can probably figure out, if there are minor arcs, then there should also be what we call major arcs. So a minor arc being less than half the circle, a major arc then, of course, would be the opposite of that. Instead of less than 180 degrees, has to be more than 180 degrees. Okay, so I want to show you that in this same picture, though, there do exist what we would call major arcs. Okay, and to find these major arcs, though, I'm going to have to piece together different smaller minor arcs and put them side by side. For example, oh, by the way, there was one more minor arc that was still in this picture. See how if you add 60 to 30, how that's 90? So the arc AC is a minor arc, okay? But there are also major arcs. Now, major arcs, when you go to name them, you cannot simply use two letters. In fact, every minor arc that was in this picture has a corresponding major arc. Remember when I started with the minor arc AB? Well, there is also a major arc version. The major arc would start at A and work its way all the way around to B this way. So instead of the short way from A to B being 60 degrees, we're going to go from A to B the long way. Okay, so in order to name a major arc then, like I said, you can't just use two letters, because if I use two letters, you have to assume you're going the short way. So to show I'm going the long way, act like you're tracing this. Still begin with the A and B, though. All you're going to do is throw one extra letter in the middle here that indicates you're going around the long way. So you have the choice in this case of picking either the point D or C, because you could call this A, D, B, or you could call it A, C, D. Or CB, sorry. Okay, the A and the B, of course, again, are the beginning and end, so you have to use the A and the B. It's just you got choice of C or D in the middle. I'm just going to pick C in this case. Again, we put an arc above it. The little M would indicate measure. So how big would that be? Well, if the short route was 60 from here to here, what would be the long way? Well, you could add up, 120, 150, and 30. You could add all those up and see what you get. But of course, if you keep in mind a full circle is 360 degrees and that part is 60, The long way around then should just be 300, right? 300 plus 60 is 360 degrees. And what do you know? When you add these up, look what you get. You do in fact get 300. Okay, so that's a major arc when you're going the long way around, and it should be more than half the circle. There's more major arcs that we can find up here. You know, let's try at least a few more of these. For example, what if I said find the measure of arc ACD? Not ACB, but ACD. Again, if you follow the letters in order, A, C, D, you see that starts here and works its way all the way around to here? ACD. Okay, so again, you could just add up 60, 30, and 150. Or, if you notice, ACD is everything except for this part that was 120. So if you just take 120 off of 360, that's another way to find the exact same answer. So you can just do that simple subtraction or add these three. You know, if you add, let's see, what do you get here? 9, 14, carry the 2, 240. And what do you know? That's what you get when you take 120 away from 360, 240. Okay? So again, that's a major arc. And again, every minor arc has a corresponding major arc. It's just the other, the rest of the circle, you know, the long way around. Okay? Now, there's a third possible arc. If you think about it, you could have arcs that are less than half the circle, more than half the circle, but the third option is you could actually have an arc be half the circle. Now, we don't call it minor or major. When it's exactly half the circle, and I bet you've heard of this term before, it's called a semicircle, or some pronounce it semicircle. Okay, a semicircle is exactly half, so it will always measure 180 degrees. No more, no less. Okay, in our picture here, we do have some semicircles as well. Now, like a major arc, though, a semicircle should be named using 3 letters. Because, again, it could get confusing if you only use 2 letters. And, of course, semicircles would be created anytime you see a diameter. Diameters, remember, cut a circle in half. So when you look at this picture, DB is a diameter. Okay, it's cutting the circle in half. So we have 2 semicircles. We've got one that runs up across the top here from D to B. And we have one that goes across down here through the bottom from D to B. Okay, so that's why we can't just call it DB. You know, if I just called it arc DB, I don't know if you meant the top half or the bottom half. So when you go to name these, you should be using 3 letters again. And again, just like on a major arc, act like you're tracing it. So this top semicircle would be DAB. Dab. And of course, its measure then would be 180. It's exactly half the circle, a semicircle. The bottom half, instead of being called DAB, would be called DCB. And again, it would also have a measure of 180 degrees. Okay, so semicircles tend to come in pairs. I mean, if you cut a circle in half, it's going to have 2 halves. You know, in this case, an upper half and a bottom half. If there were a second diameter, then of course there would be 2 more semicircles. And so on. Every time you draw a diameter in there, you'll create 2 more semicircles. Okay. So that's all about arcs, minor arcs, major arcs, and semicircles, and how they find their measure. So just remember, the measure of any arc is always the same as its central angle that intercepted the arc. So 60, 60, 30, 30, you know, this angle here would be 120, and that would be 120, 150, 150. And by adding up the arcs, like we were doing here earlier, by the way, we're making use of one of the postulates in this chapter There's a postulate 9-1. I didn't bother to write it up here because it's really common sense. You know, you got arcs side by side. When you put them together, you're just going to add together the two individual arcs and create a bigger arc. But it's postulate 9-1 if you want to look it up on your list of postulates and theorems. And it's called the arc addition postulate. Okay, it's a lot like way back when we started this class. If you remember right, there was a segment addition postulate. So this is the arc addition postulate. All right, now I want to cover a few more ideas here for notes and stuff, and then maybe try just a few more problems, and then we'll be done with this section. But one of the ideas I want to show you, first of all, is what's called concentric circles. You know, if you break down that word concentric, we talked about this earlier this year. Co is a prefix that means together. So these are circles that are together, sharing the same, yes, you guessed it, center, concentric. So they're together with sharing the same center. The best everyday example of this that everybody can relate to would be like a bullseye. You know, you've got a center point here of this circle, and then there's a bigger version here that has the same center, and a bigger version here that has the same center. Okay, those are concentric circles. It's also like when you drop a rock into a pond, and of course the pond has ripples that go out, and those ripples are circles. You know, they get bigger and bigger and bigger. They're concentric circles that have the same center point where the rock was dropped in. Concentric circles I want to bring up because if I were to draw a central angle, let's say, like this angle here, let's say I just made a central angle that's 90 degrees, in fact. Well, then I want you to see that because these centers are all sharing that same angle and center, that the arcs that were created also have the same measure. You know, even on this little circle here, this arc right here from there to there, that's 90 degrees. Because if that was 90, if the central angle is 90, the arc's 90. Same with this arc right here. Okay, that arc is also 90 degrees. See this arc right out here on the biggest circle yet? That's also 90 degrees. So the measure of the arcs is not dependent on the size of the circle. It's just dependent on that angle, the central angle. If the angle is 90, all these arcs are 90. But I hope you understand then that the arcs are not congruent. We would not say they're congruent. In fact, in order to be congruent arcs, then they would have to have the same, not just the same measure, you know, 90 degrees, but they actually would have to have the same length. You can see this one's longer than, say, this shorter one in here. Okay, so congruent arcs they have to have the same measure and length. Okay, so be careful there. These arcs have the same measure, but not the same length, so they would not be congruent. By the way, for circles just to be congruent, in general, the whole circles, okay, they have to have, of course, the same radius. So in these circles, none of these circles are congruent either. Again, that one's real small, medium, bigger, and they all have different radius, different radii, different radiuses. Okay, you can see this one with the smallest, and then it keeps getting longer and longer. Speaking of arc length, by the way, there's a formula for this that we can use that they don't bother to give you in the textbook because they figure that you should be able to figure it out on your own. Okay, because if you think of the length of this arc, not its measure in degrees, but its length. You know, like if I took a tape measure and measured how long it was. Well, that length is really just part of the length of the whole circle, which is circumference. So if you remember right, circumference, we had a formula for was 2 pi r. Okay, so if that's the circumference of the whole circle, if I just want to know the length of an arc, then what I'm going to do is I'm going to take that circumference and I'm going to multiply it by how much of a circle I actually have. Now, how am I going to figure that out? Well, based on the measure. Okay, I know that a full circle is 360 degrees. Okay, so if I can figure out how many degrees my arc is, that will tell me how much of a circle I have. So I'm just going to put a little m in here for the measure that we talked about a second ago. Okay, measure, not length, but measure, and in degrees. So if you know the measure of the arc, you could divide that by 360. That tells you how much of a circle you have, and multiply that times the circumference. And that gives you then arc length. Okay, so we're figuring out part of the circumference, essentially. Okay, you'll want that formula because that'll come in handy on your homework. You're going to have a good handful of problems that you'll have to use that formula for. Here, I'll test it out just to show you how it works too. Okay, so let's say that I want to know the length of this arc AB. Okay, and suppose that I knew this radius right here is, let's go with 5 centimeters. Okay, so I'm going to plug in a 5 centimeters for the radius. And the measure, remember, was based on that central angle. If the angle was 90 degrees, the arc was 90 degrees. So we have 90 degrees out of 360. Or you might say 1/4 of a circle, because 90 out of 360 reduces to 1/4. Okay, we're going to plug all that into our calculator. So I'm going to let the calculator do all the work. Don't forget to use your pi key on your calculator. It'll help for accuracy. Okay, so I'm going to take 90 divided by 360 times 2 times pi and times 5. Okay, you can just plunge it in straight across like I did there. 90 divided by 360 times 2 times pi times 5. Okay, and if I hit enter, there's my answer. Now, of course, you're going to get some big long decimal because you multiplied by pi, remember? Anytime you multiply by pi, you'll get a big long decimal. So my rule of thumb, round it to the nearest tenth. So in this case, that'd be about 7.9. The radius was labeled in centimeters, so that's what this would mean as well. So the length of arc AB, not its measure, again, we already knew its measure was 90. But its length, if you were to measure that then, if this is 5 centimeters, that length is almost 8, 7.9 centimeters. Okay, so that's the formula for arc length, so make sure you use that on your homework. Taking a look here to see. I do want to mention that even though not all circles are congruent, you could say, though, that all circles are similar. Remember our last chapter was talking about similarity, how they have the same shape but are just different sizes. So all circles have the same shape. You know, they all have that perfectly circular or round shape, and they're just different sizes. So circles are always similar to themselves, but not necessarily congruent. So these are all similar. All right, well, I think that's pretty much it. I mean, I showed you a formula for arc length, and that, and we talked about different minor and major arcs and semicircles and their measures. So I think that's enough information that you should be able to do your homework in this section. Okay, so for section 9-2, the homework is on page 456, problems 20 through 36 evens, and 43 through 49, do all of those. Okay, and like I mentioned in my last video, I'm going to cut back on the office hours because nobody seems to really be utilizing them. But like I said, I hope that's a good sign. Hopefully you're understanding how to do these. But if you do need to get a hold of me, if you do want to meet with me through Zoom or something like that, where I can show you problems on the board here, just let me know. You could contact me by email or send me a text through Remind. Next week, next couple of weeks worth of lessons, we'll slow down a little bit. I think I'm going to have, instead of a lesson a day, I think I'm going to slow down to a Monday, Wednesday, Friday schedule. And it'll help us finish out this chapter. And when we get through this chapter, though, then sad to say, we're done. So I hope you've been staying safe. And my next video then will continue on in chapter 9. And it's, again, going to be about circles. So I'll catch you then.